Surprise, 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 mathematicians. Surprise. I said I wasn't gonna live stream today, but obviously that's not true. I'm still going hiking, but that's gonna happen tomorrow. So here I am today to not solve your basic undergrad problems and yap about advancement.
I'm still going hiking, but that's gonna happen.
As I do. Morning, Edit Smith. Okay, so I know yesterday I was yapping about graph theory again, but I feel like I didn't get to finish saying everything I want to say about this. What did we say? So, yeah, let's come back to these questions. So, why does it seem like so we know that the rank of cycle space is this number. And why does it seem like, at least verified computationally for the cases 2, 3, 7, why does it seem like, so definitely this is rank. Why does it seem like, hello, Luis, El Petito. Why does this seem like this is the number of ways to decompose into 5 cycles? Seemingly. I don't know. It's very weird. It is also the number of 5 cycles containing any one given vertex. Now, there's a couple other things I want to point out. For any graph, if you take a spanning tree, then so let's consider an example. Let's look at this graph, for example. So a spanning tree is a tree which involves every vertex and is connected. I did cancel out office hours, but then I uncanceled office hours because I'm gonna go hiking tomorrow because it will be less rainy, presumably. Actually, dare I check the weather, how quickly it changes in the mountains? This is the most exciting part of stream where I check the weather. What do I mean by office hours? That's a good question. I mean, oh wow, it's supposed to snow today now where I'm hiking. And then tomorrow it'll just be cloudy. Man. How is it a high of 14 and a low of 4, but also snowing? Crazy. Anyways, what do I mean by office hours? In my mind, I would have thought that this was going to be like an ordinary office hour, like, when your professor or TA has office hours for a class where you go and it's just a chance to go and ask them questions and whatnot. And people do ask questions about all sorts of random things in here. But also a lot of the time it's just me yapping about totally random stuff, like I'm doing right now. So, on that note, we have the spanning tree, and notice any edge you add to the spanning tree creates a cycle. And these cycles are called fundamental cycles. And given any spanning tree, the cycles obtained in this way give you a basis for cycle space. In fact, that is the way, it is that realization that allows you to determine that the rank of cycle space will always be the edges minus the vertices plus 1. Okay. Now, what's interesting is if you look at all of the cycles, so if we take our like rooted tree picture again, right? So we look at our graph like this, right? Notice that this is a rooted tree, and so like all of the 5 cycles containing this vertex, those actually correspond to adding each of these edges in this particular spanning tree. So there's an interesting connection here, right? It's like the number of, or the full, just like the set of 5 cycles containing a given vertex is a basis. And in fact, it's a basis, and it's a basis that's in particular consisting of the fundamental cycles attached to this one particular attached to this particular kind of tree. And so I can't help but think like maybe there's some way to deal with these things. Like there's something special going on here, right? And then meanwhile, there's also this idea that so it seems like there's this many decompositions into disjoint 5 cycles. So maybe there's some sort of way to relate these 5 cycle decompositions to these spanning trees, or to these opposite cycles, or these like opposite edges in each vertex. But it's not at all clear how one would go about doing that, right? Like starting, like you pick some vertex, and now for each edge opposite that vertex, somehow you have to create a decomposition into 5 cycles. I mean, it just doesn't seem, I have no idea how to actually carry it out. Yeah. It's interesting. I mean, there's also the fact that if you look at any one, all right, yeah. I mean, could it be like, maybe you could argue that the decompositions into what's up, Abu? What's up with you? What's up here today is we're talking about some graph theory. You wish you could make sense of all of this. Well, I'm talking I'm talking loosely about crazy stuff that I started talking about yesterday. So maybe it will help if you watch maybe it'll help if you watch yesterday's live stream and then get caught up. But if you have any other kind of math questions you want to ask, feel free. You can ask about this or whatever else. Yeah, so I also then wonder, well, maybe the set of decompositions into 5 cycles, maybe that itself forms a basis. Maybe that itself forms a basis for cycle space. But I think yeah, hard to say. What am I trying to show? Well, let me go up. Ultimately, there's a problem in graph theory. Can't remember if you asked this before, but could you indicate briefly how borels correspond to choice of positive roots? Um, I will try. I will try. Yeah. Um, so let me just review this problem real quick. So we're trying to find a graph where each node has k edges for some fixed number k. Coming out of it, there's k squared plus 1 vertices. The length of the smallest cycle in the graph is length 5, and the diameter is 2, which means if you start at any vertex, you have to be able to reach every other vertex in 1 or 2 jumps. There could be longer ways to get there as well, but you definitely need to be able to do it in 1 or 2. And so here are the graphs. So we know that it's true for k equals, the only numbers that could be true for are 2, 3, 7, 57. It is true for 2, 3, and 7, unknown for 57. And it seems by inspection, so not by general proof, but by looking at these cases separately, it seems to me that the number of ways to decompose the graph into disjoint 5 cycles, so here's 2 different ways to do it for the Peterson graph, it appears to be this number. It appears to be given by this quantity. This is the general formula. And what's weird to me is that this is also the dimension. If you look at okay. So before I say any more, I get into the rambling. The question is, why is it this number? Why is it this number? Can we find the general proof that works for the missing, still unknown graph of 57? That's ultimately my goal. Okay, but let's talk about the Borels and the choice of positive roots. So let's look at, we can just look at GLN, make our lives nice and easy. Look at GL2, right? So, in general, more generally, there's a correspondence between subsets of, not quite positive roots, but maybe I should. I'm getting ahead of myself with standard parabolic. So okay, let's look at GL2. What is our sort of our standard Borel look like? It looks like these upper triangular matrices, and it factors as such. Right? So you can imagine sort of the corresponding Lie algebras, right? So here we have this torus, and here we have this like nilpotent part here. So the torus, its corresponding Lie algebra is like our Cartan subalgebra, or we can already just like the torus is already a thing that breaks up into the root system. Once we choose positive roots, we can classify parabolics contained with that Borel. You assume the specifics would follow a similar idea. Yeah, it is a very similar idea, basically. So like, let's see, what are our root in the case of GL2? Now we have now we have two different roots, right? We just have like E1 and E2. It's a little bit simpler. Um, well, I guess you could argue that well, literally speaking, SL2 is simpler, but yeah. So I guess here, um, yeah, it's like which I guess if we're gonna cut these roots in half, like which root are you going to call um positive? Oh wait, do we still need to write it as E1 minus E2? Um let's do SL2. Let's do SL2. All right, so we've got alpha and minus alpha, just two roots in our root system, right? Where alpha is this thing. And uh yeah, so going back to this picture, right? Like the corresponding Lie algebra here, of course, would be so I guess I should write this as this is our torus. Oh, hey, do proof books help in advanced mathematics? Um, Not totally sure I understand what you mean by that, but I mean, in short, yes. Well, you need to know how to prove things to be able to do advanced mathematics, definitely. And all advanced mathematics books are filled with proofs. Um, so, in that sense, yes. But maybe I'm not totally sure exactly what you're asking. If you want to, feel free to clarify. Yeah, the root system. Yeah, that's true. The root system of GL2 is the same as SL2, but with an extra unreduced dimension. Yeah. Uh, Books like How to Prove It or whatever. Yeah, I mean, well, those books lay the foundation. I mean, you've never touched one like that. Yeah, actually, neither have I. Neither have I. Because I've just learned how to prove things through my courses. Wow, OneNote is getting. Oh, I probably need to delete everything. Um, Let me just go ahead and delete this whole page. Maybe that'll fix it. Um, hey, how's it going? How's it going, Gweth? Or Gwaheth? Gwaheth? Efarf? Yeah, OneNote's really not happy with me. Uh, Indeed, coffee consumer gang showing up for duty to consume. Might even have some tea later too. Who knows? It's just random letters. Spell it however it seems best, you guess. Well, if it's best, then there's no arguing with it. Okay, let's see. Can I just delete this page now? No, it won't even let me kill it. Wow, this is brutal. Um, no, this was supposed to be a day off, but then the weather shifted. But then, well, it's not that shifted. It was going to be rainy at the peak of our hike, and apparently, it's the top of this mountain is pretty dangerous when it's slippery. So we figured it would be safer to push back the tickets a day. Um, and uh, and now apparently it says it's going to snow today. On the mountain. So I wonder what that'll make conditions like tomorrow. But tomorrow, it was supposed to be a mix of sun and cloud. Now it just says cloud. We'll see. Yeah, this is rough. This is rough. We're totally done. We're totally cooked here, gang. OneNote's not working for us at all. Um, yeah. Well, I don't know what we're gonna do if OneNote is totally cooked. Close the program. That's right. Kill it. Kill it with fire. Windows. Kill it with fire. We need to talk about Borel subgroup. I mean, I guess we can go to. I guess we can just collectively read. Let's give it one more shot. Um, what do I think of toposes? They're cool. I guess I don't really know a ton about them. Um, I mean, I have McLean and Mordrick's book, um, Sheaves in Geometry and Logic. Oh, it's a mistake trying to open this thing again. Okay, we're just gonna have to go read about Borel subgroups. Wow, that's brutal. Or topoi, as some people might say in plural. But yeah, I mean, I'd love to understand it more from the logic side of things. And now where's even my search thing? They changed my search bar. Life's hard. Yeah. But you know, topos theory is also immensely important for also things like cohomology theories that allow us to prove the Weil conjectures and stuff. So, um, you know, technically, certain things I do are in the étal topology, although I've never really had to mess about with the details of it. Um, People argue about toposes, topoi, but Growth and Deke actually just use topos for plural. Well, too bad. I like topoi. He can't do anything about it. A friend of mine doesn't agree that 0.9 repeating is 1. Well, he's wrong. I don't know what to tell him. Tell him to go watch my video on the on 0.9 repeating equal to 1. The point is the point is he doesn't even know what 0.9 repeating even means. Actually, I had a really bad take on Reddit a couple weeks ago, and I got flamed in the comment section. And maybe people are right. You don't need to go to the full um, theory of Cauchy sequences, but you should at least explain to your friend the epsilon delta proofs and what it actually means for a series to converge. Because again, the center of his the fundamental aspect of his misunderstanding is that he doesn't know formal mathematics and he doesn't know what the definition here. This is the video. Are the real numbers real? You sent him are the real numbers real? Oh, well, I don't know. There's some people you just can't argue with. I mean, I yeah, I don't know what the antidote is. At some point, you just got to give up and not spend your time arguing with people about things who can't change their mind. It's not worth your time. Oh, he hasn't watched it yet, though. Well, I mean, maybe it won't change his mind. I have no idea. Books like Hammark or others who write proofs on real analysis, linear algebra. I don't know Hammark, but number theory and groups will help you to write and understand proofs of other advanced math topics. Well, yes. I mean, for several reasons. Like one, if you just it'll just give you um a foundation in how to write proofs, right? You know, it's like uh before you go and write something like Game of Thrones. You're not just gonna wake up one day and write Game of Thrones. You're gonna write a lot of um, crappy stories before that, and you're gonna write a lot of short stories before that. Um, you know, like first you gotta learn how to even type. How words work and how to put letters together, and then you know it's a very long process. So yes, on the level of like getting a better understanding of how to write proofs, absolutely those books will help. But then also, quite literally, you will need those tools, and probably no matter what advanced field of math you go into, basic real analysis, linear algebra, number theory, and group theory show up many places. So also so a combination of the practice of the proofreading skills together with uh, learning actual techniques and theorems. Try to explain it to him, the formal limit definition. He was interested in math in school and is a really smart guy. That's why I want to explain it to him why he's wrong. Yeah. Well, I mean, as long as he's, yeah, I don't know, coming to it with an open mind, then keep trying, I suppose. I know some people who read such books and say it's helpful, but you also know people who just dive into real analysis or something. Yeah. Yeah, that's the thing is yeah, that's true. Um like it's probably better to just grab books on those subjects, as Rad said, and just dive right in. But let's yeah. With OneNote not working, we'll try and make our way through. Uh, let's see, we've got a root systems here, parabolic subgroups. Right. So here, this will probably be even fancier version because we're going to be thinking about things over different fields, right? So, right. So Borel subgroup. So first, we're going to talk about a Borel subgroup is if you pass to the algebraic closure. The definition is that's a smooth connected solvable group with a parabolic. Yeah. The group G trivially has Borel subgroups. Wait, is that what? Huh? Oh, because we're over the algebraic closures. Oh, so of course. Okay, sure. Yeah. And hence G always has at least one. Yeah. Let's find our correspondence here. Aha. Okay. Right. Oh, there's stuff going on in the chat. You think you will hope to take my idea of making videos about things or questions to heart? Would you help? Can I help you fact check them related to the subject issue at hand? Yeah, I don't think so. That sounds like a lot of work. I have a hard enough time fact checking my own videos. They should be based on fact anyways. Yeah. So yeah, I don't know. Start simple. That's maybe my advice. What are the prerequisites for the book that I have open? Probably some algebraic geometry. I mean, it introduces you to the functor of points perspective, but like, is this the best place to learn it for the first time? I don't know. Yeah, I don't know. You know what? You should just jump right into this book because there's also things. There's like all this background that technically you do need, like all this stuff about groups and forms and over other fields and root systems and stuff. But then like if you go and you jump ahead to like the sections on the representation theory, I mean you can just black box a lot of these things about, like you could just jump over to the Adels and start reading about them. But like, okay, probably generally stuff from undergrad, like a decent level. You're comfortable with AG at the level of Hartshorne, then you should be fine with algebraic geometry in this book. Like you'll probably want some other things like measure theory and blah blah blah, but yeah, don't worry about it. You should just dive in, and backfill things as you need. It's a pretty good book, pretty readable, I would say. Also tempted to make some videos. Great. We'll spawn a whole collective. How's PhD qualification exams like at my university? Do we have real and complex analysis, algebra, and topology like most? No. It's kind of weird the way we do it here. It's like, you have like your course, your required courses, and and he tried to get the book I was using, but it's too expensive. Yeah, fair. It's a good book. It's worth getting. Good morning, Nerd Coke. But yeah, so the way ours work is like you need, as part of your requirements, you need a certain amount of courses from list A and a certain amount of courses from list B, which are just like list A are like the compulsory courses we want to make sure every grad student has. And then, but you also need to, or it's like, you need a certain amount of exams from list A and list B. And then what it is if you want one of the exams to be like your qualifying exam, then you need to talk to the instructor ahead of time, and then you get like a special version of the final exam, and that's basically your qualification exam, your qualifying exam. So which I kind of like, because you're sort of forced to take the course ahead of time, and it prepares you ahead of time. So give critique. Sure. I mean, if you send me some of your videos when you make them, I might watch some of the videos and give you feedback from my modest channel. Yeah. Okay. So, where are we here? So we have our centralizer of the torus, maximal split torus, to describe all minimal parabolic subgroups. So those aren't necessarily Borel, but they will be Borel when the group is quasi-split. We find a maximal torus and describe all minimal parabolic subgroups containing the centralizer of some torus. So we actually take, we take a base for our root system. So it's not just, the base will determine a set of positive roots, but the base is sort of an even stronger thing. It's a special subset within the positive roots. Right. Oh yeah, and they say that in the next line, right? Consider the positive roots with respect to that base. Then there is a unique minimal subgroup containing the unipotent radical, where you see the Lie algebra. This is before OneNote started crashing. This was the analogy I was the example I was trying to draw in SL2. You basically look at the root spaces generated by those positive roots. And so that's going to be our unipotent radical. And so you basically you have your maximal torus, and you have this piece generated by the positive roots, and that's how you that'll be the unipotent part, and you just smash those two things together, and they'll be the products of those things. So that's, at least you can see every choice of positive roots, how that process goes. And so, in fact, yeah, this is how the bijection goes. It's once you fix the root system, it's, in fact, it's all the bases that are in bijection with the minimal parabolic subgroups. So it's basically just the Lie group, Lie algebra correspondence. Yeah, but I think maybe it's maybe, yeah, things are maybe weird with the, if we're working over arbitrary fields, maybe things get weird and janky with the exponential map. But yeah, more or less, it's the same idea. You're reading Milne and Springer, and it seems so much more complicated. Maybe they do it much more generally. Yeah, I don't know what assumptions are being made here. But also, yeah, I think well, yeah, it could be they're I don't know, trying to build up a more sophisticated machinery in those books, and maybe in this book, which is this is a very still relatively new book, a more modern exposition. So they're trying to just get things explained as quickly as possible to go and run and do things. Whereas I think both Milne and Springer are trying to develop a more full theory of algebraic groups. Okay. You study second year computer science, second year bachelor's right now, and it's a 4-year program. Very math heavy compared to other computer science programs. So far, you're really interested in the theoretical stuff. So far, you've loved complexity and computability theory, algorithms, really like abstract algebra, taking set theory, and some type theory next year's electives. Cool. That's a fun combo. Do I have any suggestions on what to learn in your free time when it comes down to the more pure mathy fields? Let's see. So you liked complexity, computability, and algorithms. I'm not. I don't know as much about those worlds. I'm less connected to those things, so I can't help you so much there. But if you really liked abstract algebra and you're taking set theory and some type theory as next year's electives, you might be interested in homotopy type theory. And generally, like, I would, maybe you could be interested in like proof assistance, foundations of mathematics, type theory, and homotopy type theory. So those are things that I would maybe look into, because they kind of blend a lot of these ideas together. So maybe that could be a thing to look into. I know it doesn't come up much in my videos, but do I have any interest in logic? Any favorite result from mathematical logic? I mean, this is so boring, vanilla, but like, of course, like Gödel's theorems. That's so like, it's like live, laugh, love of mathematics or something. Just very pedestrian, but well, I mean, I do have a video where I talk about like large cardinal axioms. I'd love to know more about that. I'd love to one day understand, speaking of topos theory, understand topos theory enough to know about the interpretation of Cohen's forcing argument in terms of topos theory. Yeah, I'd be interested in those things. I'm also, yeah, actually, there's a lot of things. I mean, I'm also interested in constructive mathematics. Yeah, I guess the topos theory perspective on logic, just in general, I would love to understand more. You could see me being a logician in another life. Yeah, definitely, 100%, 100%. And I mean, proof assistants, those are cool. You didn't like learning the subject from Springer? Yeah, I mean, it's a dense book. It's a very technical book, and he tries to build up the theory like quite generally. Um, yeah, but I think it's also good. Like, if you really, I mean, yeah, especially if you want to go on and do other things. But it is nice because he really gets down to the nitty gritty of it. Um, Yeah, I mean it's hard to beat Springer in terms of like if you really need to unpack things and like drill into it. Um good reference book to get in the weeds. Maybe I should do some lean live stream sometimes or some other proof assistants like Egda for hot stuff. I should. Yeah, it could be I thought about doing something like where it's just like I go through and try and prove stuff and I start right from installation because I know that's always a nightmare. Like it'd be such a boring stream, but it would also be probably helpful to a lot of people to see me running stuff from the command line and trying to go through the nightmare of installation. Um, Yeah, that could be good. So again, so many ideas, so little time. The last couple days I meant to record videos and yeah, I just didn't feel like it. I just didn't feel like it. Um Off topic, but when I can I explain what's the motivation behind the Ext and Tor functors? Yeah. I wonder if now that I've waited a moment, I probably need to like restart my computer and go back to OneNote. Yeah, nah, I thought, yeah, I'll have to wait for another day. I guess I'm not streaming tomorrow, so, but maybe the day after, if you remind me, I'll talk more about Tor and Next. Maybe I can just talk about the motivation for them. Oh, is it working? Okay, I'm gonna risk deleting this other page if it doesn't freeze. Die with fire. Die with fire. Ooh. Um, Do I think everything in math like sets, linear algebra, real analysis, and topology can be visualized? But what about limits or topology? Can they be drawn or understood abstractly? Sure. I mean, anything can be visualized. It's just a matter of how accurate of a representation that is, right? Um, like a 27 dimensional sphere is a very difficult thing to conceive of. But we still have ways, we still have hacks. You know, abstract metric spaces are difficult things to conceive of, but you can still like draw a circle. Yay, OneNote's working. You can still draw a little circle, and even though this is clearly like a picture in R2 in our real world, we still use this to maybe represent some totally crazy metric space, right? So, um, depends what you mean by can be visualized. Yes, but with decreasing levels of accuracy. Um, Started off wanting to do logic, but the professor mentoring you told you it's kind of out of style in modern math. Yeah, it's true. I mean, it's a real thing you need to think about. Like people, only certain areas are hiring. Like I remember when I was applying to grad school, I don't remember if it was during master's or PhD. Like I was really interested in F1 geometry, and I remember I reached out to someone who had that in their research interests. I was like, oh yeah, I'd be interested in working with you. And he's like, sure. He's like, look, if you like, I'll take you on as a student if you're interested. Like, apply. But he was like, just know that like not a lot of people are doing F1 geometry. There's just not a lot of job opportunities. So that's a very real thing to be aware of. Um, Yeah. Do I have any videos on proof assistance? You thought yesterday I heard you say this. Yes, I do. I have a video. Where is it? It's called Hot Boy Summer. Yeah, here we go. Hot Boy Summer. Um, where I talk about homotopy type theory and proof assistance. Hello, Arcturus. You've seen some visualizations for Galois groups in lecture notes. Yeah, Galois groups are definitely things you can visualize. Hello, Julie. Arad's intuition for derived functors in general comes from homotopy theory. We don't really care about chain complexes, but rather their homology. Hom tensor do not automatically preserve homology. So the derived version is like a universal correction. Yeah. Oh, and the underlying infinity category. Well, I don't know anything about that, but yeah, I mean the most basic thing about the most basic interpretation of say the Ext or Tor, as I'm sure you've probably seen before, it's this idea of like, well, we have an exact sequence, right? And that has a pretty good interpretation, right? Roughly, that means that B can be understood, or rather, C can be thought of as some quotient of B by A. You're going to prove the Riemann hypothesis? Probably not. You outlined a proof method, and honestly, you might spend a snippet and tell you to review it and see, okay? I'm not going to look at it because you definitely haven't. I don't know. You haven't even demonstrated that you can prove basic math, let alone the Riemann hypothesis. So I'm sad to hear that you're saying that, because it sounds like you're diving deeper into crankery, and I was hoping I could help pull you back from the edge of that. So so we'd like to preserve an exact sequence, right? If you have some functor, one might even naively suspect at the beginning that an exact sequence is a categorical kind of thing, and so you might even think that maybe functors will preserve exact sequences, right? But of course, this isn't the case, and a classic case is the tensor product. So it is not always true that if you apply the tensor product that it will preserve exact sequences. However, so if we have right, ABC, say these are modules, and I don't know, we tensor by some D, what will be true is that it will be preserved on the one side. We will have this sequence will remain exact. But now the question is, I mean, of course, if you have something that's not exact, right, you could just like quotient out by something to make it exact, right? Like I mean, the whole idea of, like, say, the first isomorphism theorem is that if you have some homomorphism, right, you have some homomorphism, of course, you can restrict to the image, right, and then that will make this exact. And then you can also mod out by the kernel and make this exact, right? So you can make things exact, right, by putting sort of the right object in map here. And so the question is, what do we put here to make this exact? And then in the same way that like the size of the kernel tells you about the failure of injectivity, sort of the size or maybe dimension of this object could tell you about the failure of your tensor product to be exact. And indeed, that's kind of the whole point. So turns out the object that we put here, this is Tor1, of CD. And indeed, Tor1 of CD, together with the special map that goes here, is exactly the object that you put here to measure the failure of exactness. And then Tor1 BD will go here, and so on and so forth, right? And so, in some sense, it's a measurement of how bad your functor, your tensor product fails to be exact, right? So you could say view the n, so like the largest n for which, say, this is non-zero, uh, is gives you some sort of way to quantify the failure of exactness here. So that's one thing. Okay, there's all sorts of other interpretations to give to this. Kind of asked this before, but thought you should specify, do I know any introductory RT books? What's RT? Sorry. RT, classical theory of RT of finite groups. Oh, representation theory. Yeah, I mean, I've said before that I haven't seen a ton of books that I'm actually in love with, but there's actually, I think there is this one book I have looked at it before. Oh, didn't mean to bring that up. I think it's called Invitation to Representation Theory. An invitation to representation theory, yeah. And actually, I have consulted this before because of some stuff I was playing around with the symmetric group. So I would recommend this. Might not be a bad idea to start here. There's also Sarah's book, but I feel like that's maybe not the best first introduction, but it's also not a bad book to have, and it's a nice read. Yeah. Any recommendation? Oh, you can recommend your professor's notes. He does geometric representation theory. William Crawley Bovey. William Crawley Bovey. Math notes. Geometry of representations of algebras. Is it that one? That's maybe not. Maybe he's got others. But let's just find his webpage. Preprints. Ooh, knitting. Is he knitting like hyperbolic surfaces and stuff? Are these all? Does he have notes for all of these? Research, editorial work. Ooh, cool pictures. Very cool pictures. What is this notation? I want to understand it. I don't know where his notes are. Oh, archived materials, probably. I just have to wait for the time it happens. Maybe today you'll consider a basic mathematical induction proof. Then you might consider supporting you after that. You won't regret it. Well, we'll see. As long as you, give it an honest try and keep an open mind and be open to feedback and criticism and the possibility that you could be wrong. I'm willing to give you another shot if you send me some basic mathematics and see if you can prove it. I would still say try and prove the original problem I posed to you, but we'll see. But I think it's important to stay humble and open, and I'm willing to give you another shot. This is a personal opinion, but you think it'd be valuable if someone makes some basic graduate math courses available on YouTube. So it's kind of nice, like a video library for everyone to access. I mean, there already are a ton of basic graduate math courses on YouTube. There's probably more hours than you could watch in a lifetime already. Um, you'll be trying to do it at least it helps amateur mathematicians or maybe other PhD students. Yeah, I mean there already is a lot, but we could always use more. Yeah, weird how everyone wants to prove Riemann hypothesis, but no one wants to work on showing that piano arithmetic is inconsistent. Well, a way cooler crank project. Yeah. Yeah. Lectures on representations of quivers? Question mark. Are you asking me if I know of any? Because I don't. If I go to his courses, there are notes for all of them. I see. On teaching. I see. Let's go. Teaching. General information. Teaching. There we go. I see. So if I click on any of these, there'll be notes. I see. Does he have representations of finite groups? It looks like it's mostly algebras, which is fine. I mean, that's all cool and interesting. But I think the original person was asking about finite groups. Just thought it might have been the suggested lecture notes. Oh, I see. Yeah. Love Richard Borchard's channel, and he has a lot of good content. Also seems like a sweet guy. Yeah, absolutely. Did I study something about lattice-based cryptography? No, never. I have no idea what's going on there. And my coffee's just about done, so it's about time to get going, get started with my day, get started proving. Not sure about lectures, but Dirksen Wayman book on quiver representations is great. I will keep that in mind. So time to go prove things about quivers, I guess. For you,